Welcome back everyone. In this lecture, we will continue with the study of group action. In particularly, we will study about the stabilizer of a given element or given subset and then prove they are indeed subgroups of a given group. And then using that, we will actually conclude more about the orbit of some element. Okay, so let's start with fixing some notation. So let G be a group. So this is acting on capital X, let's say via this tau. So tau is actually a group homomorphism from G to Sx. Okay, so note that given G in G and given X in X. So we denoted the image, okay, tau G of X by this G dot X. So this is the shorthand notation that we have been following. Okay. So now for given element X in X, recall motivated from the study of this orbits. So to count number of elements in the orbit, we seen that this stabilizer of this particular element actually plays an important role. So motivated from that, we define this stabilizer of this element X, which also we denoted by Gx. This is those elements in G such that G dot X equal to X. So those elements of G that fixes this X. So that is called the stabilizer of this G. Okay. So in general, we can define this stabilizer for any subset of capital X. So the stabilizer of this capital T, okay, with respect to this group action G. So it is those elements of G that fixes all elements of this capital T pointwise. Okay. So that is called stabilizer of this capital T. So then it is easy to verify that. So there is a close relationship between the stabilizer of the subset capital T and stabilizer of its elements. So what it is, the stabilizer of this capital T is nothing but intersection of stabilizer of all these elements that come from this capital T. So this is more or less by definition. I will leave it you to check. Okay. So now we claim this stabilizer is indeed. So here is a lemma. So this stabilizer is indeed actually a subgroup of G. So for X in capital X, this Gx is a subgroup of G. Note that the stabilizer of capital T is nothing but intersection of stabilizers of X, X in T. So intersection of a subgroup is a subgroup. So in particularly stabilizer of T is a subgroup. So as a corollary, we get this is a subgroup of G. Okay. So let's prove this. So let two elements G H inside G X. So then by definition, G dot X should be X and then H dot X should be X. Okay. So now look at this particular action of H inverse on H dot X. H inverse dot H dot X is going to be exactly equal to H inverse dot X. But H inverse H dot X, when you use this group law, this is H inverse H dot X, but H inverse H is identity. So this is going to give you E dot X, which is X. So that implies H inverse dot X is also fixes this element X. So now what's about G H inverse? When you apply it on X, so G H inverse dot X will be G dot H inverse dot X. Okay. H inverse dot X is X and G dot X equal to X. So that implies that this is exactly equal to X. Okay. So from G dot X equal to X and H inverse dot X equal to X, we get G H inverse applied on X fixes X. So that means what? That means G H inverse is an element of Gx, and this is true for all Gh in Gx. So that implies Gx is a subgroup of capital G. So this is what we wanted to verify. Okay. So now from this immediate corollary is stabilizer of any subset is indeed subgroup of G. Note that these are all just subgroups. Okay. So we can't say anything about the normalizer property. Okay. So now let's go back to our orbits and then try to understand them. Okay. As we noticed, okay, we are interested in understanding orbit of any element, okay, for x in capital X. So we have this orbit which is all possible images of x under the action of capital G. Okay. You take G dot x for all G in G. So this is the orbit. So now what we want to do, we want to actually say that these elements of the orbit can be counted using G modulo Gx. Okay. So let us define a map G to orbit of x. So that is the map that sends G to G dot x. So this is some map pi. So now what we are going to say, this pi is actually quotients through this G modulo Gx. So that means what? It induces another map pi tilde which is from G modulo Gx to Yx. Again the map is given by the left coset Gx sent to G dot x. So we have to verify this is a well defined map. We indeed prove actually this is gives you bijection. Okay, pi tilde is a bijective map. Okay. So once we prove it is well defined, then it is clear that by definition it is surjective map. So let us verify this is actually well defined. So what we need to verify, if suppose if you take two cosets, so then we need to say that that's mapped to single element, okay, if they are equal. So if you start with two cosets, let's say G Gx and then G dash Gx, then that should imply that G dot x is same as G dash dot x. But note that G Gx equal to G dash Gx gives us G inverse G dash is inside Gx. So this is by definition. Okay. So that means, so this implies G inverse G dash dot x is x, because Gx is the stabilizer of x. So all elements of Gx fixes x. So in particularly this element also fixes. In particularly we have G inverse dot G dot x equal to x. Now by applying G on both sides, we get G dash dot x is equal to G dot x, which is what we wanted to prove. So G dot x equal to G dash. This can be traced back. Okay. So this is if and only if, so by multiplying by G inverse on both sides, okay, or applying the map tau G inverse on both sides, we get this. So now this is if and only if we can see that G inverse G dash fixes this element x. So that means if and only if G inverse G dash is an element of Gx. So that is if and only if the left coset G associated with G and G dash, they are equal. So that proves this map is indeed injective map. Okay. So this proofs tells you that pi tilde is not only well defined, it is well defined injective map. Okay. That is what we proved. So now this is also surjective, because given any G dot x, you consider the respective coset G Gx that will be mapped to that. Okay. That means pi tilde is indeed a bijective map. So it is a purely set theoretic map, and this is just a bijection. Okay. So that means the cardinality of G modulo Gx, whatever it is, that is same as this orbit x. In particularly if G is finite group, G is a finite group, so then we have the cardinality of G modulo Gx is same as the cardinality of Ox. Okay. But since G is a finite group, using Lagrange's theorem we can see that the cardinality of G modulo Gx is nothing but the index of Gx inside G, which is exactly the cardinality of G divided by cardinality of Gx. So, this tells us that how to compute the cardinality of the orbit. So, the cardinality of the orbit is exactly equal to the index of this Gx inside G, which is the ratio of this cardinality of G divided by cardinality of Gx. So, this is called orbit stabilizer theorem. So, which actually tells us how to count this number of elements in this orbit. Okay. This is very useful formula. Let us say we have some unknown set capital X which we are interested in counting. Okay. For some reason, let us say we know that that set is finite. So, we are interested in counting. So, then to count that set we can use this powerful tool that is called group action. So, you find a nice group G, you make that group act on this capital X. Okay. Then counting the number of elements in this capital X is nothing but counting the number of orbits and plus the number of elements in each orbit. Okay. So, that is what that orbit decomposition theorem tells. Okay. So, X can be written as disjoint union of orbit X, where X comes from some indexing set capital lambda. Okay. So, in particularly if you are interested in counting the number of elements in capital X, so then this is exactly equal to the number of elements in OX where X runs over this capital lambda. So, we need to know two information. So, what is this capital lambda? The indexing set of this set of all orbits and the elements of the each orbit. So, then the cardinality of X will be exactly equal to the cardinal sum of this cardinality of this orbits. So, now using this orbit stabilizer theorem, you can see that the cardinality of OX is given by cardinality of G divided by cardinality of Gx, okay, assuming that G is finite. Okay. So, now if everything is finite, let us say X is finite, okay, and G is finite, in that case we can make very precise statement about the cardinalities. So, the cardinality of X equal to summation cardinality of G divided by cardinality of Gx, where X is coming from capital lambda. But if you think about it, this summation can be divided into two parts. So, let us see how one can do. Okay. So, what we have cardinality of X equal to summation the index of Gx in G, where X runs over this capital lambda. Now, what we do, we divide this capital lambda into two sets, capital lambda naught disjoint union capital lambda 1, let us say, where capital lambda naught is those elements X in capital lambda such that the cardinality of G is same as cardinality of Gx. So, basically this quotients that becomes trivial. And then what is capital lambda 1? Capital lambda 1 is nothing but the complement of capital lambda naught, for which the quotient is really strictly greater than 1. So, this sum now you can see that can be written as the cardinality of capital lambda naught plus summation the cardinality of G divided by cardinality of Gx, where X comes from capital lambda 1. Okay. Let us unreveal what is this set, which is those X in lambda such that the cardinality of G equal to cardinality of Gx. So, if you think about it, the number of elements in the orbit, it is exactly equal to the number of elements here in this coset, the cardinality of G modulo Gx, okay, which is same as the cardinality of G divided by cardinality of Gx. If the stabilizer is full, if and only if this orbit becomes cardinality 1. Okay. So, Gx equal to G if and only if the orbit has one single element, namely X, because X is always there. So, that means, so you are collecting this lambda naught, these are all just orbits having single elements. This lambda 1, those are all orbits having more than one element. Okay. So, if you think about it, what is the meaning of this orbit having one single element or stabilizer being equal to G? That means G dot x equal to x for all x in G, sorry, for all G in G. Okay. So, that means those elements of capital X, that those elements that are fixed by all elements of capital G. So, that is the meaning of these things. Okay. That has a special notation. So, we can define what is called this fixed point elements, which is denoted by x power G. So, this is what? This is those elements x in capital X such that they are fixed by these elements of capital G and all elements of capital G. So, that you called fixed point subset under this action G. Okay. So, then using this notation you can see that you can rewrite this star as follows. So, how one can rewrite that? So, this star becomes cardinality of x equal to cardinality of x power G plus summation mod G divided by mod Gx, where x is coming from this lambda 1. Okay. So, this is the equation that we have. So, recall what are all the things that are involved in this equation. Okay. So, x power G is there, that is those elements of capital X that are fixed by all elements of capital G. So, that is the fixed point subset. And what is this lambda 1? Lambda 1, those elements of this orbits, okay, or the indexing set of the orbits such that the cardinality of the orbit is bigger than 1. So, the cardinality of orbit is bigger than 1, which is equivalent to the cardinality of G is strictly greater than cardinality of Gx. Okay. So, only such elements we are taking, and using this we are saying that the cardinality of x is exactly x power G, the cardinality plus summation cardinality of G divided by cardinality of Gx, where x comes from the special set lambda 1. So, in case if we know that, okay, how to find this x power G for given group action G, and then if we have information about all subgroups of this G, okay, or information about the group G, all information about the group, then using that we can actually compute the cardinality of capital X. So, that is what it says. Okay. So, this is very important equality or counting principle. So, we can have plenty of applications of this. Okay. So, we will actually give many applications of this result in next class. So, before that, so let us actually define some more terminologies that are associated with this group action. Okay. So, here there are more things. So, for example, when G acts on capital X, okay, so then this, that is via this tau. So, then tau is actually a group homomorphism from G to Sx. Okay. So, now once you have a group homomorphism, you can define what is called the kernel, okay, the kernel of tau. The kernel of tau is those G in G such that tau G is just being identity X. Okay. So, what is the meaning of that? This is those G in G such that G dot X equal to X for all X in capital X. So, you are looking at all possible elements of this capital G such that they act as identity element on this capital X. Okay, that is called the kernel. Note that kernel is a normal subgroup of G. Okay. Suppose if you are able to produce very nice group action on something, and then whose kernel is actually non-trivial, then G must have normal subgroup of that particular action. Okay, this is something very useful. This also we will use it later, and we also defined these stabilizers. So, Gx for x in x. So, those are also very important. Again, we also defined what is called the stabilizer of T for any subset of x. So, these are all important things, subgroups that are related with group action. So, now on the other hand, so given any group action, what one can do, one can also make any subgroup to act on that. Suppose tau is a group action, that is a homomorphism from G to Sx. Sometimes for some subgroup of this G, call it H, we can restrict this map to H. Then that is going to give you again group homomorphism from H to Sx. Then this is with this restriction we call gives you restriction action on this capital X. So, basically G is acting on capital X, you are restricting that action to capital H. From this you can see that H also acts on capital X. So, this is also something very important, we will see later. And on the set side we have the orbits. So, on the group side what we had the kernel and then all these stabilizers. On the set side, so we have these orbits. And we also have this fixed point subgroup, and this is something one can generalize even for any subgroup of G. So, that means, so what I am trying to say, like you can define this x power small g for example. So, then that is nothing but those elements of capital X such that that is fixed by this G. So, this is fixed point subset of this G, and note that x G will be same as x subgroup generated by G. So, this is something I will leave it you to verify. So, these are all some terminologies that will be used later in order to understand any group action. I will stop here and we will see some application of what we proved today. So, later in the next class. I will stop here. Thanks.